my name is Kieran and I teach applied maths at the Academy. I'm in the middle of projectiles, which is question 3 on the applied maths paper. And I'm doing section 1, which is called horizontal planes. We're talking about projectiles on level ground. Now, this is the last lesson in that particular section. And it's to do with something called I and J vectors. Now, I and J vectors are very, very convenient. You'll actually find them very convenient when we do collisions next. Let's take an example. Let's say I've got a car, something, traveling at a speed of 10 meters per second. They're going in a direction at 30 degrees to the horizontal, or 30 degrees to the x-axis. Or you could say east 30 degrees north. You could say it in lots of different ways. So there's a picture representing this particular situation. I'm going to represent that velocity vector by that particular arrow there. It doesn't matter if you put the arrow at the end or in the middle. So the size of that vector, u is equal to 10. Now I'm going to break that up into components. I'm going to break that up into an x component and a y component. So my x component is this component along the x-axis, and my y component along the y-axis. And you know how to get those components. You know what ux is. Ux, the x component, is equal to u cos 30. U is 10, so we're talking about 10 cos 30. Put that into my calculator. And when I put it into my calculator, I get 5 root 3 meters per second. I also want to work out the y component. And you know what the y component is? Uy will be 10 sine 30. Put that into my calculator and I get 5 meters per second. So here I've got ux is 5 root 3 and uy is equal to 5. Now let's talk about the I and J situation. Here's a very clever idea. Let's get a little vector called I. And let me place it along the x-axis. And let me make it exactly 1 unit long. The way I'd write that down mathematically is the size of I is equal to 1 unit. Let me also make something called a J vector. The J vector is a vector of 1 unit that I'm going to place along the y-axis. So the size of J, write it down like this, is equal to 1 unit. Now I have a very clever, neat way of writing down the vector u. You see, that's a bit of a mouthful. I'm talking about u, 10 meters per second, in a direction at 30 degrees to the horizontal. I can now write it down like this. I can now write down that the u vector is equal to 5 root 3 I vectors, because remember the length of each I vector is 1 unit. So I can write it down as 5 root 3 I vectors plus, so I go out there 5 root 3 I vectors and then I go up 5 J vectors. So plus 5 J vectors. I could wrap that in brackets and put the units outside it. Meters per second. So it's a very elegant way of writing down a vector. As I said, instead of saying, oh, it's traveling at 10 meters per second in a direction at 30 degrees to the horizontal, I can now write it down as a beautiful mathematical expression. You know, if I was to write that down in general, I would write it down as u is equal to ux I vectors plus uy j vectors. And you know, every single vector can be written down like that. So for example, I could write down the velocity vector as Vx I vectors plus Vy j vectors. I could write down the displacement vector, S, is Sx I vectors plus Sy j vectors. It's a very nice way, and it's got huge advantages. And many of those advantages you're going to see when we do collisions later on. Now, let's see if I want to get back from that I and j vector, and I want to get back, what angle does it make? What is the size of that vector? Well, I could use Pythagoras. So for example, here you've got this vector here. Let's say I say to you, well, what was the speed originally? Well, I call that the absolute value of the u vector. And how do I work it out? Well, I'm going to work it out from Pythagoras. So if I want to find the length of that side there, the hypotenuse, well, you know it's 10. We know the answer, so I'm just showing you how to work it out. Well, it would be the square root of that side squared plus that side squared. It would be the square root of, what's the bottom side? 5 root 3 squared. And what's the other side? 5 squared. Put that into your calculator and you will get an answer that is 10 meters per second. Also, let's say I want to get the angle back. I know we know the answer is 30 degrees, but how would I find it out if I didn't know that? Let me call that angle, for example, theta. Well, I could say tan theta is equal to the opposite side, and the length of the opposite side is 5, divided by the adjacent side, which is 5 root 3. So I could say tan theta is 5 over 5 root 3. That breaks down to 1 over root 3. And then theta will be the inverse tan of 1 over root 3. Put that into your calculator. And of course, you know what the answer is. The answer will be 30 degrees. So in general now, you can say this. If I'm given a vector like that in its I and j format, well, if I want to work out what was the size of the original vector, also called the magnitude of the vector, I write it down like that. Well, it's equal to, using Pythagoras, the square root of the number in front of I squared, ux squared, plus the number in front of j squared, uy squared. So that's how I find the magnitude of the vector from its I and j format. And what happens if I want to find the angle? Well, tan theta. Remember how we did it over here? Tan theta is the opposite side. The opposite side represents the j vector, and the adjacent side the I vector. So tan theta is that number in front of j, uy, divided by ux. So if you want theta, you can get the inverse tan of uy over ux. So that's what I and j vectors are all about, and we'll be using them quite a lot in the Applied Maths course. Now let me do an example. So you're in your notes on page 2. And I'm going to look at worked example number 2. So I'm going to go over to this board here and do the example. So it says the velocity of a particle is given by u is equal to 5I plus 12j meters per second. So there's my particle being fired off with that initial velocity. Forms an angle theta, it goes through the air, and it lands. All the usual stuff that we did in the previous 4 lessons. But this lesson is about i's and j's. So, part 1. They're asking me the question. Find part A, ux. Well, you know immediately, in general, U can be written as UXI vectors plus UYJ vectors. You can see exactly what's going on there. You can see the value, the X component is 5, and you can see the Y component is 12. So UX is equal to 5 meters per second. And in part B, Uy is equal to 12 meters per second. And they're also asking me to find tan theta. And we know that tan theta is equal to Uy divided by Ux. So in part C, tan theta is equal to Uy, that's 12, divided by Ux, that's 5. So that's part 1, which is straightforward enough once you understand what's going on with I and j vectors. Part 2, we're asking the question, after 1 second, find Vx and find Vy. Well, the time t is 1 second. What's the formula for V? The formula for V is equal to U plus AT. To find Vx, we're talking about that in the x direction. Now you know what the accelerations are when we're talking about horizontal planes. You know that the acceleration in the x direction is equal to 0 meters per second squared. And you know that the acceleration in the y direction, AY, is minus 9.8 meters per second squared. That's always the case. And of course, because AX is 0, you know that Vx is equal to Ux. It doesn't matter what the time is, the final speed is always the same as the starting speed, it never changes. There's no acceleration in the x direction. So that implies that Vx is equal to Ux, which is 5 meters per second. Part B, they're asking me to find Vy. So Vy is going to be U plus AT in the y direction. That means Vy is equal to Uy, which is 12, plus AY minus 9.8, and we're talking about after 1 second, by 1. So 12 minus 9.8, I get 2.2 meters per second. Because of those numbers, I kind of know where it is. You know, Vy is still positive. That means it's still on the way up. If Vy was negative, that would mean I've passed the halfway point and I'm on the way down. So approximately, I would say V is there. After 1 second, let's say we are there. If I drew in the vector for V, which is a tangent to the path, there is V. What about Vx and Vy? We'll break that into its components. There's Vx along here. And that's equal to 5. And Vy is positive. It's this vector going here. So Vy is equal to 2. So they're asking me in part C, what's the inclination of the particle to the horizontal? Well, let's call, there's your V vector there. There's the horizontal. Let's call that angle in there alpha. So once again, we're talking about finding tan alpha in part C. So tan alpha is, well look, you know every vector can be written in 9j form. So tan alpha is the y component over the x component. It's going to be Vy divided by Vx. So Vy is 2.2 and Vx is 5. Let me put that into my calculator. I'm going to get, well, they're asking me, in the previous part they asked me for tan, Keesha. Here they're asking me for the inclination of the particle to the horizontal. In other words, they're talking about the angle. So I'm talking about finding alpha. Alpha is the inverse tan of 2.2 divided by 5. Shift tan, fraction 2.2 divided by 5. And, make sure that you're always active when you're watching these lessons. You're using your calculator, you're using your notes. So let's say about 23.75 to the horizontal. Moving on, they're asking me to find Sx and Sy. Well, you know the formula for S is equal to ut plus a half at squared. So I'm going to apply that in the x direction and the y direction. So in part D, S equals ut plus a half at squared. Could apply that in the x direction. And of course you know this already, don't you? That when you're dealing with horizontal planes, ax is 0, so I can more or less forget about that last term. So Sx is equal to ux, which is 5, by, we're talking about after 1 second, so I get 5 meters. And part E, I want to find Sy, so apply that S formula in the y direction. So Sy is ui, which is 12, by 1 second, plus a half ay. Well, I told you to remember this from previous lessons. Minus 9.8, half of that is minus 4.9. So it's going to be minus 4.9 by 1 squared, which of course is 1. So put that into your calculator, and you get an answer of 7.1 meters. You know what they represent? They represent the coordinates of where the particle is after 1 second. So what does Sx mean? It means the distance you went out along the x-axis. And what's Sy? It's the distance you went up. So Sx along here, that's 5. And Sy, that's 7.1. In other words, I can now write down the coordinates of the point where that particle is after 1 second. Its coordinates are out 5 and up 7.1. And then on to the final part. The final part, they're asking me to find the time of flight. They're asking me to find the horizontal range, and they're asking me to find the maximum height. Well, the time of flight is the time it takes to land. You know, what have we been doing so far? We've been doing an analysis of what happens after 1 second. So now, I want to see what happens when it lands. So remember what we do when we do these kinds of problems? We put our table down. And this is the table for a landing. It lands. And you have the x side of the table, ux, ax, sx, and I have the y side of the table, uy, ay, and sy. Ux, ui, we got them earlier, 5 and 12. Ax and ay, always the same for talking about horizontal planes. 0 and minus 9.8. Sx, well, Sx is the distance if it lands. So you're talking about Sx being this horizontal distance here, and that horizontal distance there, that's what's called the range. So when it lands, Sx is the range. And of course, if it lands, then the distance in the y direction, that will be 0, won't it? 0 meters above the ground. It's at the same level as when it was launched. So therefore, Sy is equal to 0. So look, I've got full information there. I want to find the time it takes to land. So I'm going to use the S equation. S equals ut plus a half at squared. And I'm going to apply that in the y direction. 0, uy, 12 by t, that's the time of flight that we're trying to find, plus a half ay, that's a half of minus 9.8, that's minus 4.9, t squared. There's a quadratic in t. Now I said yesterday you can divide across by the variable t, because one of the answers is a trivial answer. Time is equal to 0, that's at launch, where Sy is also equal to 0. So you can divide across by t, and then you can jump that term to the left. So I get 4.9t is equal to 12, and t is equal to 12 divided by 4.9. Let me put that into my calculator. I'm actually going to leave it as a fractional form for a particular reason. If I put that into my calculator, I get 120 over 49 seconds. You could work it out to one decimal place, but I'm leaving it like that for now, for a particular reason. So that's the time of flight. Now, moving on. The next part, we want to find the range. So in order to find the range, I'm now going to go to this side of the table. I'm going to apply the same formula. So on this side of the table, well, let me actually do it over here. So I've got S is equal to ut plus a half at squared. In the x direction, and of course you know this, don't you? Ax is 0, so we can completely forget about that part. So when it lands, Sx is the range. Ux is 5. And the time? Well, the time, both sides share the same time. So the time it took to land is 120 over 49. So it's by 120 over 49. Okay, so that looks like a little bit tricky. So let me just decimalize that to 1 or 2 decimal places. So I get, say, 12.24 meters. Last part, they want us to find the maximum height. So just go back to my diagram here. I mean, that's a perfectly symmetrical curve. The highest point it reaches is right in the middle here. So this here, that represents the maximum height, which I'm going to call h. Now, how long does it take to reach the maximum height? Well, we mentioned this in previous lessons. It actually takes half the time for the time of flight, half the time to land, it reaches its maximum height. You can prove that by putting Vy equal to 0. We did it in a previous lesson. So let me write down the time it takes to reach the maximum height. So that time is half the time of flight. There's my time of flight there to land. Half of that, divide 120 by 2, I get 60 over 49 seconds. So now I'm going to apply my formula, S equals ut plus a half at squared, in the y direction, and I'm going to apply it at that time. Well, if I do that, what's the distance in the y direction after that time? It's what we call the maximum height, which I'm going to call h. It's equal to uy. Uy is 12 by time. 60 over 49 plus a half AY, you know that's minus 4.9, by t squared, by 60 over 49 all squared. So I'm going to put all that into my calculator, and that will give me the maximum height. So let's say 7.35 meters. Let's move on to example 3 from your worked examples on page 2 from your notes. So what they've given me is a particle is projected from a point O. And the initial velocity is given in I and J format as 9.8I plus 19.6J meters per second. What they want you to find, first of all, is calculate the angle theta at which the particle is launched. Well, as usual, let me fill in the table. So, what's ux? Ux is the I vector. It's 9.8 meters per second. Uy is the coefficient of the J vector, 19.6 meters per second. And of course, if you're talking about horizontal planes, AX is 0 and AY is minus 9.8. I can't put an SX and SY in because I don't know where it is, has it landed or whatever. So the first thing they're asking me is calculate the angle theta at which the particle is launched. Well, you know every vector can be written down as U vector, UX, I vectors plus U, Y, J vectors. And how do I pull the angle out of that? Well, tan theta is Uy divided by Ux. From my table, Uy is 19.6 and Ux is 9.8. Put that into your calculator and you get an answer of 2. So what are they asking? They're asking me to find the angle theta. They're not asking me to find tan theta. So theta is the inverse tan of 2. Now that's quite elegant to leave it like that. You can work it out if you want to. Put that into your calculator and work it out to 1 decimal place. But it's fine like that. I like to leave it like that. Now going on to part 2. Part 2 says, express the velocity of the particle after t seconds in terms of I and j. Find in terms of t the direction in which the particle is moving after t seconds. So after t seconds, I don't know where it is because t can stand for any number along that path. So it can be anywhere. Let's say, for example, it's there after t seconds. So right there, that's t seconds. So they're asking me to express the velocity of the particle v right there. But of course, you can break that up, can't you, into its components. You can break that up into vx, which is going in that direction, and vy, which is going in this direction. So let's work out vx and vy. But we don't know the time, so everything will be in terms of t. So you write down your vx equation. You know that v is equal to u plus at. Apply that in the x direction. Once again, you know that ax is 0. So simply you get vx is equal to ux. And ux from my table is 9.8. vy, u plus at in the y direction. So it's v plus at in the y direction. ui, 19.6. AY minus 9.8, and it's T in general. That's how I write down Vy. Now they want me to write down that velocity vector in terms of I and j. So as I said before, every vector can be written down as like V is equal to Vx I vectors plus Vy j vectors. So in this particular case, that becomes 9.8 I vectors plus, better wrap all that in brackets, 19.6 minus 9.8 T j vectors. So that's how I'm writing down V, the vector V, in I and j form. Now they also want to find in terms of t the direction in which the particle is travelling after t seconds. And what I mean by the direction is find the angle. The angle in question would be this angle here, V, next to the horizontal. So if I'm going to find tan alpha is equal to Vy divided by Vx. Vy, we've worked out here, it's 19.6 minus 9.8t divided by Vx. Vx is 9.8. Can I simplify that expression? Well, I actually can. I can divide the 9.8 into each term on the top line. So if I divide it in, 19.6 divided by 9.8 gives me 2. And 9.8 into 9.8t gives me minus t. So I've got tan alpha is equal to 2 minus t. Now they did ask for the direction, so I'm talking about finding alpha. So alpha will be the inverse tan of 2 minus t. So there's my angle. So the next part, part 3, it says express the displacement of the particle after t seconds in terms of I and j. So I'm going to do the same thing again. So I'm going to write down, this time, instead of writing down the velocity vector, I'm going to write down the displacement vector. So S is equal to ut plus a half at squared. I'm going to first of all apply that in the x direction. So Sx is equal to ux t. And of course you know that the second term, half ax t squared, we don't need it because ax is equal to 0. So Sx is equal to ux, which is 9.8. And the time is general, so it's by t. Do the same for Sy. Apply that equation in the y direction. Uyt plus a half ay t squared. Ui 19.6 t plus a half ay. You know what a half ay is? It's minus 4.9 t squared. So now I'm going to write that down in I and j form. So you can write down S is equal to Sx I vectors plus Sy j vectors. And now replace Sx and Sy by their values. Sx is 9.8t, I vectors, plus Sy, better wrap that in brackets, 19.6 t minus 4.9 t squared j vectors. So now I've written down the displacement vector in terms of I and j. They're also saying find in terms of t the direction of the displacement vector after t seconds. Well, there we are right now. So the coordinates at that point are out a distance Sx, that distance there, that's Sx, and up a distance Sy. So I can write down the coordinates there are Sx, Sy. What about what they're asking here? Let's say find the direction of the displacement after t seconds. Well, it started at the origin. So if I draw a line from the origin to the point where it is now, you see that line there? The angle I'm talking about it making is this angle in here, and I'm going to call that angle beta. So I want to find beta. So tan beta, we're now talking the angle that the displacement vector makes. Well, there's the displacement vector in INJ form. Tan beta is going to be Sy divided by Sx. What's Sy? There it is there, 19.6 t minus 4.9 t squared divided by Sx. Sx is 9.8 t. Can I simplify that? Well, the t's, that t will cancel that t and leave t there. And I can divide those numbers by 4.9. So if I divide that by 4.9 in your calculator, you'll get 4 minus t divided by 2. That's what tan beta is equal to. And what about the angle beta? The angle beta will be the inverse tan of 4 minus t divided by 2. Okay, it's not that hard, you know, but it's tricky trying to get your head around all the i's and j's and how they operate. I'm going to finish this lesson with a leaving cert question. I'm going to do leaving cert question 2006, 3-part A. So we'll do it over on this board here. So a particle is projected from point O with a velocity u 9.8I plus 29.4j. We've got in part 1 expressed the velocity and the displacement of the particle after t seconds in terms of I and j. So we're doing exactly the same as we were doing in the previous question. First thing I would do is fill in your table. Ux, well, once again, you know that every vector can be written down as Ux I vectors plus Uy j vectors. So you can see what Ux is. Ux is 9.8 meters per second and Ui is 29.4. The usual Ax and Ay, 0 and minus 9.8. Once again, they're talking about after t seconds. So after t seconds means it could be anywhere along the path depending on the value of the time t. So I want to write down the velocity and the displacement vectors in terms of I and j. Well, v is equal to u plus at. Vx is equal to ux, because you know that at, that will be 0. Ux is 9.8. Vy is u plus at in the y direction. That's equal to ui 29.4 minus 9.8 t. I want to write that down in INJ form. Well, v can be written down as Vx I vectors plus Vy j vectors. Vx is 9.8. I plus Vy, better wrap it in brackets, 29.4 minus 9.8 t j vectors. So there's the velocity vector written down in terms of I and j. I want to do the same with the displacement vector. So s is equal to ut plus a half at squared. Apply that in the x direction. Sx equals uxt. Don't need that term, sure we don't. Ux 9.8 times t. S in the y direction. Uy 29.4 times t plus a half ay minus 4.9 t squared. Now I can write down the S vector in I and J form. It's Sx I vectors plus Sy j vectors. That's equal to Sx 9.8t I vectors plus Sy 29.4t minus 4.9t squared j vectors. So I've written down V and S in terms of I and J, and that's part 1. Part 2 says, find in terms of t the direction in which the particle is moving after t seconds. The direction in which it's moving. You're talking about that direction, alpha. Tan alpha is equal to Vy divided by Vx. Vy divided by Vx, there's my expression for Vy. That's 29.4 minus 9.8t divided by Vx, which has a value of 9.8. Can I tidy that up a little bit? Well, divide the 9.8 into that term, and it goes in 3 times, minus t. So I've got tan alpha is equal to 3 minus t. So that's my answer to part 2. This is expressed in terms of t, the direction in which the particle is moving after t seconds. Well, I suppose they did say the direction, didn't they? So direction really means angle, so I suppose my answer should properly be alpha is equal to the inverse tan of 3 minus t. So when they say the direction, I suppose I better give the angle. Part 3. Find the 2 times when the direction of the particle is at right angles to the line joining the particle to O. You see this line here? That point there, of course, represents Sx, Sy. I called this angle here beta in the previous problem. I think we'll do that again. What they're actually asking here is, we want to find the times when that line there is perpendicular to that line there, that blue vector, the velocity vector. In other words, I want to have a right angle in here. Well, you know what we're going to use here? We're going to use slopes. Because the one thing about tan, when I get tan alpha, that's the slope. That's the slope of that blue vector. And tan beta, that's the slope of that broken line there. So let me find tan beta. Tan beta is to do with the displacement vector. Tan beta will be Sy divided by Sx. Sy, 29.4t minus 4.9 t squared divided by Sx, 9.8 t. You can divide the t into each term above. You divide that number into each above. Well, actually, I'm going to actually divide by 4.9. So divide all the numbers by 4.9. So I will get 6 minus t divided by 2. That's what tan beta is. 6 minus t divided by 2. So the question they're asking me in part 3 is, find the 2 times when those directions, the direction of that broken line and the direction of the blue vector, are at right angles to each other. Now you know from your coordinate geometry that perpendicular slopes multiply together to give minus 1. Tan alpha is the slope of the blue vector. Tan beta is the slope of that broken line. They are the slopes. If you multiply tan alpha by tan beta, the condition for them to be perpendicular is they have to be equal to minus 1. So tan alpha, that's equal to 3 minus t. If I multiply that by tan beta, 6 minus t divided by 2, that's equal to minus 1. So we're going to solve that for t. Slide the 2 up, get minus 2. I'm going to multiply these brackets out. 3 by 6, 18. Do the t's in my head. Minus 6t minus 3t minus 9t. Minus t by minus t plus t squared. Look, you do the algebra whatever way you want to do it. I do it my own way, so you might have to do 2 or 3 lines. That's up to you. But basically our answers will always be the same. That's a quadratic equation in t. Let's bring everything to one side. Plus t squared minus 9t plus 20 is equal to 0. That looks like it might be factorizable. 2 brackets. T squared is t by t. 20, 5 by 4. They both have to be minus to get minus 90 in the middle. Put each bracket equal to 0. So I've got t is equal to 4 seconds and t is equal to 5 seconds. They're the 2 times when the directions are perpendicular to one another. Okay, so quite a long lesson, I and j vectors. You're now finished horizontal planes in their entirety. You've done everything. We did 5 lessons altogether. It's quite tricky. I'd actually argue that horizontal planes to part A could be harder than the part B questions. Now that you're finished, in terms of leaving cert questions, I call this the course work you're going to do, CW. You can do all the leaving cert questions. Now I've given you leaving cert questions from 1996 to 2019. That's more than enough. There's no need to go back before 1996. 1996 to 2019, you can do all the 3 part A questions. There are questions on horizontal planes. Also from the notes, if you want more practice, you've got 3 exercises. Exercise 1, 2 and 3. Okay, so thanks very much.